Okay, so welcome to you all. Today, starting from today, for 3 days at this time of the day, we will have some NMR lectures, which will be given by Dr. Leonid GRUNIN. Dr. GRUNIN is our partner in our RISE project, Such Equality, from Resonance System. He is a physicist and he builds up NMR systems from scratch, actually. And we have been working with him almost 10 years. And if our lab is at currently has an NMR knowledge, we owe a lot to Dr. GRUNIN. So we got really significant progress with his approach and with his systems. So I would like to thank him again here. And for these 3 days, we will have valuable lectures from him. And just to keep you all informed, we are going to record the lectures. So if you have any objections, just let us know, because this is something that we need to let everybody in advance. And yeah, I'm gonna give the floor to Dr. GRUNIN and your lecture can start.
Okay, great. So I'll try to introduce everything, but I guess I need to share the screen. Host disabled participants screen sharing. This is what I.
Okay, now you can.
Now, yeah. Looks like I can do it. Yeah. Okay. Dear ladies and gentlemen and everybody. So today and tomorrow and the day after tomorrow, we are going to go through the main topics of time domain NMR, which is crucial for our such equality project. And we will mostly focus on the things that we are focusing mostly in our activity and actually in the activity of the secondaries that we have here. This is time domain NMR in solids, in condensed matter, and mostly in solids, to give you a review and to show you the advantages of this fantastic method. So let's start. For today, we will try to go through the following topics. I'm not sure we will be able to go through all of them, but I guess we will try to. And then what's important is just to maybe hear some questions from you that are highly welcome. So we will briefly make introduction to what NMR method is, what it normally consists of, what directions of NMR are existing. Then we logically will come to time domain NMR instrumentation and signals and the peculiarities of measurements. And then we will go through the very basics of the theory that is behind the signals and the values about structure that we get from a sample. And then we will possibly go through standard applications for you to be able to see how this knowledge can be applied. Also, we will try to organize the direct show how the sample tubes, how the samples themselves can be placed into the NMR, and how the live signal of a solid sample looks like. So let's go on. So all analysis of different materials, different compounds, can be split into principally different approaches: the physical approach and chemical approach. Chemical is classical one. Everything started from chemistry. When you have some compounds, you mix them, something is evaporating, something is going down, and then you do some measurements. But with the development of different methods, different electronics and mechanics, it was possible to produce also physical chemical methods of analysis, and the NMR is definitely a part of it. So physical analysis normally does not destroy sample itself. It uses different physical effects. So here I just enumerate some classical approaches like microscopy or chromatography or colorimetry or even X-ray. These are all types of analysis of from physics. And one of them, I guess, the most useful is the most widespread is spectroscopy. Spectroscopy, then it means that we are dealing with some sweeping of frequency of something. If we take a brief look at the ranges of different types of spectroscopy, you can see, I don't know whether you can see my mouse. Actually, good question.
Yeah, we can see it.
You can see it, great.
Yes.
So you can look at the range of radio frequency. So this NMR relates to radio spectroscopy, radio frequency spectroscopy, and it occupies the wavelengths from 1 meter to 5 meter from point of waves, and just really small part of that range belongs to time domain NMR, which is from nearly Earth field up to the modern time domain NMR, up to the frequencies that are reachable with the permanent magnets. And what's important from this picture, once the frequencies are really low, comparing to most of other methods, spectroscopical methods, it means that the influence, the impact of this radiation that we use it onto the human health is the lowest one. It means that if you use your mobile phone, it influences your brain and your body much stronger than an NMR device. Let's go on. The whole NMR direction can be split into sub-directions. The most well-known is high-resolution spectroscopy, high-resolution NMR. It is done in frequency domain. This is because this is direct spectroscopy. High-resolution NMR is the most demandable method in the chemical analysis. And if we try to calculate the amount of Nobel Prizes in chemistry and in physics, the highest number of these Nobel Prizes somehow relates to the NMR spectroscopy. So it means that NMR is really promising method. So other directions are so-called low field NMR relaxometry, which is done in time domain, which we also call time domain NMR, that we will talk today about. This also can measure not only NMR characteristic, but direct parameters like material diffusion coefficients. And let's say the third direction of nuclear magnetic resonance is imaging. This is what you all possibly know from MRI measurements, tomography. It gives spatial domain measurements, but we are not going to focus on that at the moment. So let's move on and get very simple estimation of the high resolution NMR. Before all that, the basic physics. I'm sorry, but we need to focus sometimes today on the physics, otherwise we will not understand anything. But I guess all you know that in quantum mechanics, particles or waves, they are being considered as the level systems. And if you take some quantum mechanical levels, then picture is the following. Some, mostly for all known chemical elements, some of isotopes of them have the magnetic moments, nuclear magnetic moment. Nuclear magnetic moment, it means that it is a magnet, and if you place it inside the the external magnetic field, these moments start behaving in an interesting way. So when you apply the field is off, nothing is happening. When you apply the field, the main level of this nuclear spin polarization is split in two, and the distance between these levels, you mean the distance where transitions can happen. When we have several level system, it is always the case that transitions are happening So and you can somehow observe radiation of the photons, and you can capture them and you can measure the effect. So the splitting of the levels, in other terms, this is energy. In other terms, this is frequency, is directly proportional to the electromagnetic field. So the stronger magnet we have, the stronger energy level distance we observe. And this effect in terms of megahertz is the following: the highest so-called gyromagnetic ratio. This is the proportion, the coefficient between frequency and the magnetic field, is about 42 megahertz per 1 Tesla. For hydrogen, main hydrogen isotope nuclei. This means that if you have the magnet with a field of 1 Tesla, you will have this energy splitting at 42.5 megahertz. So, and the natural content of these nuclei, actually, hydrogen, you know, it is everywhere, and the signal for hydrogen is the strongest one, and hydrogen NMR is mostly used in all time domain machines that exist now. Of course, there are some deviations, there are some dedicated instruments, but most of the measurements, especially in science, in time domain NMR, are done with the nuclei of hydrogen. It is not bad because I guess most of the compounds in the universe, they have some amount of hydrogen. Okay, this is in terms of frequency and in terms of the main effect. Well, let's imagine that these guys, these hydrogens, let's call them for simplicity protons, they exist in a sample, in a solid or liquid, but doesn't matter, and they exist, and they have their own spin magnetic moment. When you apply the outer field, these moments align the field. Some of them look in the backward direction, but most of them look in the forward direction, and it matches the direction of outer magnetic field. So imagine we have this magnet of 1 Tesla, and these guys can be observed on the frequency 42 megahertz. And the frequency of resonance is influenced not only by the magnet, but also by the structure of the dynamics of the samples that you are measuring. And the influence is the following. So this is B0, it is of the magnet, but also you have local fields because all these guys are magnets themselves. And they produce the magnetic fields that influence their neighbors. And of course, all these hydrogens, they are not free hydrogens. All these protons, they are not free protons. They are within the atoms. Atoms are within the molecules. And of course, there are lots of electrons. And electrons, they are rotating and they create their own magnetic field. And according to the classical electrodynamics, this field will shield the outer magnetic field, and this shielding will depend on the structure of electron clouds. So these guys influence the frequency, and so the distribution of frequency in a real sample becomes informative. It carries information about the structure and dynamics due to what I'm talking about. Well, let's look. This shielding field, as I already mentioned, it is from electrons, and we call it chemical shift in high resolution NMR spectroscopy. We will not talk a lot about that. There are also some other types of coupling, some other types of interactions, like indirect coupling. And for us, it's more important that this direct local magnetic field from the neighbors. This is called direct spin-spin, or in other terms, dipolar interaction, dipolar couplings. And this is the main this is the main reason for time domain NMR. And this local field depends on chemistry, depends on molecular conformations, depends on molecular arrangement, what is important, and also on dynamics. If they move, the field is also, but they always move. Just a few words about high resolution spectroscopy. We have to say that it is critical that the shielding field is that causes chemical shifts in NMR spectra. They are proportional to the field of the main magnet of the instrument. So the stronger magnets you have, the stronger the wider will be the splitting, and so you can see the more accurate NMR spectra. And at this moment now there are magnets that are higher than 1 gigahertz. It means them really many Tesla, and they produce a strong signal, a good resolution to observe things like peptide structure within proteins conformation and many others. But to simply understand it, if you take ethanol and you put inside the NMR machine, you will get this splitting. This is like we talk shielding field. And then you will have 3 big lines, and these lines will have fine chemical structure depending on the indirect spin-spin coupling. This is the basis of high resolution NMR. You get the spectra, you process the spectra, and sometimes you make multi-dimensional spectra, and you get extremely important information. And these ranges of chemical shifts depending on the chemical structure of electron clouds. For protons, it's within ppm per million points per million, and so there are already measured library, and you can, looking at the spectrum, you can tell without drinking that this is pure ethanol or this is not pure ethanol. When we talk about time domain, the machine for time domain NMR normally is much simpler than for high resolution NMR. That's why it's more affordable for universities and for industry. The basic content of this machine is the magnet. Here I show it like 2 poles of the magnet. The magnet produces the external magnetic field, which we call B0, and then we need to put sample somewhere, and we use coil, radio frequency coil. We put sample inside the coil, and then we do excitation. We produce, the machine produces the strong magnetic field perpendicularly to the main magnetic field, and this field causes spin transitions. And then after we excite, the system relaxes. And this process is called relaxation, and we detect it through the receiver. So in all time NMR machines, there must be magnets, the probe, which assumes the coil, and then transmitter that excites, and the receiver that gets messages from spins about the structure of samples. From the point of populations in Boltzmann equilibrium, when we don't excite, we still not excited the sample, like we saw before. These guys have their arrows of spin magnetic moments along the field, and some of them have opposite the field. Here you observe the same situation. Those guys who are on a lower level, they are majority of them, they look along the magnetic field, and the minority looks opposite. When we disturb the system with a radio frequency pulse, we can do many interesting stuff. We can make the equilibrium of these levels, or we can inverse population of these levels. From the geometrical point of view, you know, now the majority in the equilibrium looks along the z direction. Normally, z is the direction of the magnetic field. When you make these populations equal, there is no z component, because these guys just look somehow perpendicular to the magnetic field, and they are just experiencing the precession. Or when you apply the inversion pulse from the transmitter, the population are inversed. And the rotation of this vector is proportional to magnetic field of the transmitter that we apply to the coil. So I think I need to say it more faster, because we will come soon to the applications, but this is extremely important. So we can rotate the total magnetization of the sample. You put the paramagnetic sample, that is most of the possible samples, in the magnet, and this is being magnetized. And after it's magnetized, you can play with this vector of magnetization, some people call it polarization, play in different way. You can rotate it, and then you observe the relaxation. The relaxation happens in two directions, actually. In direction of the main magnetic field, we call it T1 relaxation or longitudinal relaxation or spin lattice relaxation. And also relaxation in the XY plane. We call it transverse relaxation or spin-spin relaxation. So here, spin-spin, this is relaxation within the levels of spins. This is how they come to equilibrium. But when you excite the system, you understand that system is not only quantum mechanical, this is a real material. And this excitation that we did with the transmitter, it must be dissipated into structure, into network, into the lattice of a sample to give rise to the mechanical model or rising of temperature and so on. So there are two types of relaxation: the relaxation within the spin system and with relaxation between spin system and the lattice. Two types, and they are characterized by the relaxation times T2 and T1. Then here, I don't think I need to put lots of attention on this transparency, but look, when you observe the relaxation and so-called T2 relaxation, you normally see, if it's a simple material, one component homogeneous material, you see the decay. It should be the decay which is characterized by the relaxation time. The amplitude of this decay will be proportional to amount of hydrogen within a sample. It means the more sample you put, the stronger amplitude, or it depends on the proton density. And this relaxation time will depend on the dynamics. We will talk about it slightly later. For the longitudinal relaxation, this is the different curve. And here we have the constant parameter, which is called T1, that we already discussed. So the instrumentation itself, as we already discussed, high resolution NMR involves the high fields, and normally the classical NMR that is still used in most of the laboratories is that it is around 400 megahertz. I'm not talking about some specific guys that I installed in a few universities, but this guy is the really working horse of the high resolution NMR, 400 megahertz. Classical magnet for the time domain instrument machine corresponds to around half a Tesla. It's around 20 megahertz. And according to the formula that I'm showing here, the signal to noise ratio, the difference between high resolution machine and low resolution machine, this is just huge difference, and that's why lots of chemists that are dealing with high resolution spectroscopy, they even don't like to think about time domain NMR relaxation, because they claim the signal is low and what you can see there. But let's see what we can see. The ways to overcome this problem, this drawback, is to do more accumulation of the signal to fight against the noise, and also to use the modern electronics that is being developed quite fine during last decade. Other problem of time domain NMR machines is not exact homogeneity of the main magnet. Here I just show typical situation. Magnets are not parallel, and where they are closer to each other, the magnetic field is stronger. Where they are more far from each other, the magnetic field is weaker. And imagine that sample locates in all these areas, all these regions. And so here in the upper part, the frequency, which is proportional to the magnetic field, is higher, and here is lower. And then instead of the long magnetization decay, you will observe the fast magnetization decay, which is characterized by so-called T2 star. And this is another interesting feature of time domain NMR. You normally work in the rather inhomogeneous field comparing to big machines, and to overcome this, the classical echo sequences are used. So I don't want you to learn it, but this is somehow we apply some pulses and we recover magnetization stroboscopically in some points, and then these points will give us the envelope of real magnetization, real relaxation. So it's possible to overcome the inhomogeneity puzzle somehow, to overcome the low field, low field challenge, so low signal. And one more problem, especially when you are dealing with solid samples, this is so-called the dead time or reading time of the probe. Of course, coil is always connected to some capacitors, and it has its own Q factor, its own parameters that do not allow the system to recover immediately after the excitation pulse from the transmitter. And it is always so-called reading process. And this process, we call it also the dead time. It overlaps with a signal that is actually interesting for us, especially in solid state time domain NMR. And this is somehow can be resolved by using special echo sequences that we also will talk about later. So actually these three bugs, these three bad features of time domain NMR comparing to other types of NMR can be somehow compensated. Well, before going forward, I think we have too much theory. I would like to ask Esma, that is our secondary that is now in Germany, to make a simple demonstration how this NMR machine look like, how the sample, what is the sample, how you put the sample. So Esma, now I think it's your turn. I will stop. I think I will stop sharing at this moment, and Esma will share her screen.
Okay, can you hear me?
Yes, Esma.
Yeah.
Yes. Firstly, I will show the how to put our sample and our sample, something like that. You can just pin my video for a while, then I will share my screen to show the measurement part. This is the tube that we use for the measurements. We put our samples into it, just one centimeter amount, and we will put our tubes into magnet, and we will go to our software. Then I will share my screen to show how to measure. And this is the software that we use, and we can just run the measurement by clicking this.
Esma, the
button.
screen share still did not show up.
Ah, yeah, okay, let me try one more. Now, is that working?
Not yet. Okay, now it is.
Yeah, now we get it.
Okay. After we see the software, we need to upload our seconds. Then we can press this button, run button, and we can run our experiments.
So you just need to know that this is the real sample that Esma just put inside the magnet, and you are observing pre-induction decay with special echo sequence. This is starch, and this starch contains the rigid part, and this starch contains the liquid part because it sucks water from the air. So Esma can tell you that the first fast decay is from polymer, and the long part of the decay is from the water. So it's important for you to see now, because we will talk about it slightly later. Okay, measurement is done. Esma, you can demonstrate more.
Yes, and we can see the decay in a better way by going to XY plot, and you can see the polymer part up to this point, and later the longer component, let's say water, in that part. We can make fit to see how the components fits our measurement signals. We can go semi-crystalline part and make plot and report results, and we can see in a better way how it works. In this part, yeah, we can see the polymer, and after that point, the exponential part is coming from the long component. Am I right?
Yeah, yes, you are right.
Yeah.
Can you please show again the feature tab? We just need to the feature tab. You don't see it. Yeah, okay.
Now.
Okay, here you see we apply some models to feed the data, and from these models you can calculate not only water content, you can calculate crystallinity and amorphicity, but we will of course talk about details when you come here for the second month, or for you when you're trying to interpret data. So this is just for you to have the idea how measurement is organized. So the measurement itself looks quite simple comparing to, let's say, chemical methods of analysis, or even chromatography, when you need to syringe the sample inside the contour. Okay, Esma, thank you so much. Now I think I will switch back to.
Dr. GRUNIN, can I ask a question?
Yes, always.
Well, you mentioned about, I mean, for the sample volume, we said that up to 1 centimeter. Like, what happens if you overflow the tube?
Nothing bad will happen. You will see the strongest signal, but the pulses, I mean, radio frequency pulses, they will not be accurately 90 or 180 degrees for the whole sample, because some of the sample is slightly higher than the coil. And it means that applying such guys like magic sandwich echo, or maybe multiple quantum sequences, can be problematic, because they require more or less precise pulses, precise notation angles.
Okay.
But this is not a problem if you want just to look at the component ratio, because let's say for classical standard SFC applications, the samples are being filled to the top of the test tube, and also for dispersion and so on. So that's why it's not a problem.
Okay, thank you.
For most of the measurements. So now I will just briefly go through the general theory, because we will talk about the theory also tomorrow. So very, very dangerous, very horrible part is Hamiltonian. Hamiltonian is the guy that determines the behavior of those local magnetic moments of each proton. So you have to use Hamiltonians, otherwise we are not able to describe the relaxation anyhow. So, but today we are not focusing on mostly on mathematics. I'm just telling that for time domain NMR, the dipolar Hamiltonian, that direct spin-spin interactions, this is the most important guy, and this depends on the geometry. You see, on the geometry, and also if these guys are somehow moving relatively to each other, they produce changing of these angles of the orientation. And this also, the Hamiltonian also depends on dynamics. Well, so this is something that we are going to talk tomorrow, and here the dynamics itself. It's quietly essential parameter, how the molecules are moving. Here, people are normally talking about correlation function of motions and correlation times of correlation functions. So what it means, if you have any sample, the molecules are always in the motion. Some of them, let's say in liquid, they move really fast. In solids, they normally don't move to long distances, but they can somehow vibrate. Some functional groups can even rotate, and so this also can be considered like molecular motions. And the correlation times, the longer correlation time, it means that the guys are moving quite slowly. That's why the time of correlation, while one molecule is moving along the direction and passes its own size, is long. When we deal with solid, it is somehow microseconds or parts of microseconds, or maybe even longer. But the spectrum of, if we use the FFT, Fourier transform, the spectrum of these motions is quite narrow, and you see the frequency range. If we come to liquid, these guys are moving, molecules are moving really fast, and the correlation time is short, but the spectrum of molecular motions is wide. This is important to keep these pictures in mind when you try to interpret the results of NMR. Later, we will put these files somewhere, these presentations somewhere, so everybody can access them and look more. And if has questions, of course, addressed to German. All this science is based on the evolution of the so-called density matrix or density operator. Density operator describes the levels of all the spins. So the actual presentation is used also for physicists, but just talking simply, this Hamiltonian can be considered as something that contains structure and something that contains dynamics. So we can somehow look at both things, dynamics and structure. And from all this mathematics, you will come to so-called semi-classical simplification or semi-classical approximation of the main equation. So initial equation, this is called a kind of Schrödinger equation for the quantum mechanical system, which is called Liouville equation. So some of the consequences of that the relaxation rate, so relaxation is this spin lattice and spin depends on the energy spectra, like we talked just before. The energy spectra on the frequencies of resonance, so the double frequencies of resonance, and on the just on the zero frequency, and also depends on the static magnetic moment, static second moment of the line of the NMR line, which is determined by this static location of the nuclei that participates in the resonance, and is totally depends on geometry. So here I'm telling about the same things. Structure structure of the relaxation rate or times of equation depends on the motion and depends on the arrangement of spins or the arrangement of molecules. And as a consequence of this simplified, guys, so-called Blombergian parcel pound theory, when we have this simple correlation function which is exponential and characterized by only one correlation time, here the consequences of this semi-classical Redfield approach, they come to the Blombergian theory, where you have already something like correlation time. And these guys, R1, R2, these are just relaxation rates which are reversely proportional to relaxation times. So the relaxation times are determined by the second moment, it's called the structure, and the correlation times, that is dynamic, that is how molecules are moving. So the longer correlation time, the more slow motions these are, and the behavior of T1 and T2 is the following. If we talk about solid, especially if we talk about solids, the T2 normally is short and T1 normally is long. And if we go to so-called liquid part of this graph, the T2 and T1, they know in most of the cases they behave equally, similarly, and they all grow with the intensification of molecular motions. So this graph must be in all heads of all those who deal with time domain NMR. This is essential, the main graph of NMR relaxation. Well, so we can talk about relaxation time, and it looks like you put a sample and you measure to only one parameter. This is not in fact true, because most of the samples, they are heterogeneous, they have might have different fractions, like you just saw from ESMA experiments. And for example, that sample starch that contains solid fraction with a short solid fraction, and more or less water with a long T2. and then we measure one samples, and we immediately get, even for the simplest approach, we get 2 relaxation times, and we get 2 populations. So you immediately can think about, for example, humidity, or let's say, if it's not water, you can think about oil, or even some short molecules that are within the big polymers and so on. So this is not so straightforward that the time domain NMR is low informative. Now I plan to go through some standard applications for you to get an idea how these decays are used. The most, let's say, the oldest standard application is to get to know how much liquid fat is within, let's say, piece of butter or piece of something solid. If you take typical butter, it looks like, especially from the refrigerator, you will see it is like something solid, but in reality it is not true. There are some components, like, let's say, unsaturated fatty acids or triglycerides that move. Then they would form the liquid phase, but you don't see this liquid phase. But with the time domain NMR relaxation, it is really easy. You put the sample inside the NMR, and you observe the simple experiment. You give one pulse and observe the pre-induction decay. And what is decaying fast, like you saw in the starch? Here, for fats, the fast decay is characteristic for the solid fat, and the long decay is characteristic for the liquid fat. And you don't need to do any chemical exercises. You just put the sample and measure the solid fat content, like a ratio between the amplitudes of the line. For example, this is S. This is what we measure in a short. This is what we measure in a long component. But to estimate the contribution of the solid fat, we need to subtract 2 amplitudes and then divide by this S value. So this is just simple, one of the simplest applications that appeared, I guess, 30, maybe 40 years ago, maybe even more. Then measurement of the oil in seeds. This is the next standard. This is also ISO standard, and there are analogs from ASTM. You look at something with different relaxation. If you take seeds from, let's say, sunflower, they always contain some small amount of water, and they contain some amount of oil. The more oil they contain, it's much better, because you can get more oil from the harvest. And understanding that the oil has longer relaxation time and water has shorter relaxation time, you can see simple experiment of Pan-Echo and just see that the oil signal is the amplitude of echo that proportional only to oil, and the signal of FID is proportional to oil and water. And just using some calibration for that, you can measure just immediately the content of oil in seeds. So it takes about 1 minute or even less. So it means that the method is quite informative. Then I think the simplest application of time domain NMR is the total hydrogen content. Total hydrogen content, you just look at all hydrogens that are in the sample. You just see the intensity of the signal. And different, you put something inside your tank when you drive the car or when you fly with the aircraft. And these hydrocarbons, they have different length, and hydrocarbons of different length, they have different content of hydrogen. And this method allows, without using any high resolution NMR, without using any chemical things, just to get to the idea of the percent of hydrogen inside the oil, inside the fuel, and so you can get idea whether your fuel is okay or not, depending on the number that you have. Well, also this is, I think we will skip it for now, because I don't want to skip. I just tell you that it's possible to analyze porosity of of rock cores. It's possible to analyze the oil pickup of artificial fibers. You know, all what you are wearing, it normally made out of fibers. For many purposes now they become artificial, and where they are being produced, they always have some really small percent of oil. Otherwise, the friction will be too high, and they will break. And the measurement of this so-called spin finish or oil pickup is essential. It is also now nearly the standard. It's becoming standard soon in some countries. Maybe now. I will just show you. Will just see the video, and then I'll. I'll just use some introduction. These guys from Finland, they are our partners, and they are making NMR, this portable NMR, and this NMR is dedicated only to measure the water content of wood. I just invite you to watch this video. It is quite short, and so you will get your idea also about the hard rotation and the method itself. Let's look.
I think there is no sound in the video, right?
So you have seen the test tube that we use in our spin track NMR instrument, and here these guys are using really big samples. The idea of using big samples that you need to average the humidity. So different wooden chips, they might contain different water, but if you put lots of them in one cup, then you will have the average results. So I think I will skip some advertisements. So okay, I think I will stop at the moment. So just for you to have an idea how different NMR devices can be, and that calibration is in many applications, calibration is essential. So here we measure humidity, and we understand that the intensity of signal is just proportional to water content, and that's why we need for calibration only empty and a full glass of water. Then you have this line, and then you can measure the humidity. Well, so there are some other applications, and now I invite you to make a kind of very short systematic view how all these measurements, what is the background of all measurements. All time domain NMR measurements can be subdivided to absolute amplitude measurements, relative amplitude measurements, and the relaxation times measurements. So this is what we still will talk today about. And all other stuff, more romantic, will be tomorrow and the day. But let's focus on today's romantic. So for absolute measurements, you need to have the calibration. Because you are measuring absolute values, you need to know the mass of sample. Then you normalize by the mass of sample or maybe volume of sample. Actually, matched equation for matchables, right? If you put the full sample or full test tube of sample, then actually your signal is normalized by the volume, and it can be used for some precise measurements. It depends on what application you want to use. Okay, I'm coming back to the presentation. So for absolute measurements, you need to have the normalization, which is not NMR, which is either mass or volume. Then if you talk about absolute measurements, they are water content, oil or moisture in seeds, what with hydrogen, spin finish, total fat, proton density for multiple tasks. That's things that you need to something to normalize at. And there are a huge class of measurements that are relative amplitude measurements. Like today, you saw the signal from starch and from water. And here, this is what I've described before. This is the different contributions. And all these measurements are relative. So we divide something by something. And for relative measurements, you don't need to know the mass of sample. And what you can measure in standard application: solid fat, total fat, crystallinity, water constant, spin finish, or water pickup. For example, for SFC, you see the melting. Okay, what's more important for our such a quality project is to focus on sugars or starches or something other that is sweet or has lots of calories. So the amplitude ratio, here I show some free induction decays of I guess it is also starch. So the red is what you observe by the experiment. And this red curve can be deconvoluted into 3 components, like this brown, fast decaying and oscillating. Later you will know that normally all oscillating signals, they can be referred to crystalline contribution. Something fast decaying, which is green and which is amorphous, and something slow decaying, which is blue dashed line, that is normally water or whatever. And such approach of relative amplitude ratio is really good applicable to polymers like polyethylene, polypropylene, and other artificial polymers, also to natural like cellulose, starch, and pectins, and all these guys, to food things, and also to other directions.
Dr. GRUNIN, can I ask
yes.
you a question?
Yeah.
So here, when we do this decomposition, is this the semi-crystalline model that is available on the Relaxed 8 module? So is this the exact equation?
Yes, you know, here I demonstrate really we have now results from different starches and different sugars, but the model never can describe the real sample with 100% accuracy. For some samples, these models work better. For some samples, these models work worse. It depends on the sample and the model. So I always invite people to think about their own models. Just the model must be physically logical, reasonable.
Okay.
And
so
here, we will talk about this slightly later. Here, I want to demonstrate that when we have the model and it fits, it's perfect. When the model does not fit, then it's worth to think about a second moment measurements. You get just one number, but this number is reproducible, and it characterizes the crystallinity contribution. And or using amplitude ratio. So all these 3 guys, they are in the solid lab of Relaxate software. They all are realized there. So you can use model of Abrahamian or cosine function for crystalline, or you can just calculate the second moment. or you look at the amplitude ratio. Okay, I'm going on. Well, so again, all NMR, all domain NMR measurements can be absolute amplitude, relative amplitude, and measurement of relaxation times, and everything actually can be combined with each other. Relaxation times, it is more characteristic for liquid samples, though we need to mention them. There are some classical applications. We will briefly go through one of the most interesting now that is demanding, and that's lots of measurements are being done in different types of electronic, of cosmetics, of paints, of lots of different industries. When you have particles and when you have the solvent that contains these particles, and you have the relaxation, you look only on the solvent, but the solvent around particles is interacting with the particle, forming so-called interface layer that is somehow adsorbed around the particle, and the molecules of solvent that are adsorbed, they of course they have much less mobility, and we discussed that the lower mobility, the lower T2, the lower relaxation time, the higher mobility, the longer T2. So for the bulk liquid, bulk solvent, you have the long T2, and for those who are nearby a particle, they have short T2. And this model looks and works quite nicely until some considerable concentration of particles. So if you want to measure, if you want to know, for example, surface area, specific surface area of particles, you put known amount of this material, of this powder material into liquid, and then you first measure the relaxation of liquid, of pure liquid, then you measure relaxation with a couple of different concentrations, and the dependence on concentration of the relaxation rate, which is relaxation rate is reversely proportional to the relaxation time, will be linear. And well, the angle or the slope of this line is so-called relaxivity. The higher relaxivity, then the more effective this surface absorbed water. It means that it can be, for example, smaller particles, they have the higher ratio of surface to volume, or this can be the particles with somehow surface chemistry that absorb better or worse. So this guy depends on the surface chemistry and depends on the surface area. And based on such type of measurements, so here are just very simple you can measure very specific surface area that is extremely important. You just dissolve, put in the NMR, and then you get the number, the particle size, the particle concentration, and also the effectiveness of the surfactants or dispersants. Sometimes particles aggregate to each other, and then you have less surface area, but if you put surfactant, they disaggregate and you have more surface area. And this is the case that can be used for estimating the surface area. Now, relaxation times can be also implemented to analyze soft polymers. For example, rubber. Here I show two classical graphs. So some soft and especially elastic polymers, they are made out of the basement by the cross-linking of amorphous polymer chains. The stronger cross-linking you have, the more rigid this actually this rubber, and it depending on the temperature. So below the glass transition, there is no dependence of the relaxation time on the cross-linking. But when you raise the temperature, the higher cross-linking, the lower relaxation time will be. This is logically, the more cross-linking, the less motion of the segments of chains can be observable, and so the T2 goes lower because the mobility is lower. Also, you can observe the so-called interface effect. So this is a model distance from the particle of carbon black that adsorbed absorbs the molecular chains, and whilst they are attached to the particle, they have low mobility of lower T2, and they have high T2. So by applying time domain NMR, you can measure cross-link density, or you can measure filter content, and you can measure molecular distribution. So these are just, let's say, the most used approaches of the time domain NMR to measure, to get some numbers and to get some values of the dynamics and the structure. Of course, it is not spectroscopy, and it is not so straightforward sometimes. Due to this reason, to get information from time domain NMR, it is still important to study this technique for a while, for some years. Then when you have this, let's say, multi-dimensional picture, you can create your own experiments and get lots of information. So my offer now is to maybe to listen to your questions. So next days we will have more demonstration of more specific things and talk about the performance of the software, how to calculate, I don't know, crystallinity, water content, or whatever, and how this can be applied to the samples that are characteristic for such a quality project. So, Mehmet, I think you are about to moderate this discussion. So let's think about organizing the discussion and questions.
Okay, so yeah, we can get questions for Dr. GRUNIN. If you have any, I will definitely have more questions. Let me maybe start the discussion session, and then we will keep on having more questions. Well, nowadays we are struggling with a high-resolution solid-state NMR data, which we have sent you also, Dr. GRUNIN, a sugar signal. Well, as far as what we realized that the signal that we get from a high-resolution solid-state system was also really noisy. And what could be, what is the advantage of getting this solid-state data on a high-resolution system compared to our system?
So, okay, you mean
the MSD data.
So you got high resolution spectra or high resolution solid echo?
High resolution solid echo. Actually, FIDs. We have
so
FIDs.
It means that it's just measured on the machine with a higher field.
Yes, yes.
So you don't talk about C13 spectra?
No, not spectra.
Okay, this noisy, it means it's not good because the less noise, the better results.
But when we are dealing with FIDs, is it still better to work on a high resolution system? That is what I'm studying.
No, it depends on the high resolution instrument. High resolution NMR, they can be just the classical high resolution NMR for liquids and also solid state probe in the wide bore magnet. Okay. And then for spectroscopy, it must be rotated under magic angle, and the cross polarization can be implemented to look at the carbon nuclei. But it depends on what that time of the probe, what the amount of sample. Normally, if you go high with frequency, you get stronger signal, and you have much better signal to noise. This can be the advantage. So the free induction decay signals should not differ much from depending on the frequency.
Okay. Okay.
But the T1 measurements, of course, but this is a different story.
And here in this slide, you also mentioned about cross-link density.
Mm-hmm.
So still we need to always have a calibration for cross-linking as well, right?
You always, nearly in all things, you need somehow a calibration.
Okay. Okay.
You always need calibration, yeah.
Hi, Danuta.
Hi, Danuta.
Hi, may I have a question?
You may have 5 questions.
No, I have one.
Okay.
Did you try to measure diffusion coefficient in some solid systems using your equipment?
Well, diffusion. This is the main question. If you have the, let's say, if you have something like starch or cellulose and you have water inside, you can look at diffusion of water.
Yeah.
So this is definitely possible, and we can estimate the requirements to the pulse gradient in these systems. But the diffusion of self-diffusion of solids, you know, for that this is not something that we are targeting in our hardware, because this is absolutely different device with a strong gradient.
Okay.
So now clear. I guess maybe to think of generation more questions. So the participants of such a quality who are not NMR people, they can just think of telling the tasks that they might have to their samples, and then we can analyze from the time domain NMR whether it is possible to resolve this task or how to implement it. Maybe we can organize this in the following seminars in this way. So just to collect in one place the problems that exist for understanding the structure of different sugars, of different food scientific objects, and then we will try to make the reply, how to measure whether it's possible, and so on.
So maybe one more question following this line, if I may.
You still have.
I understand. Okay, you have solid-like and liquid-like fraction in a system, yeah, and then you can somehow deconvolute the signal into solid and liquid-like contributions, yeah. But this is a kind of thing, I mean, as I say, is solid-like and liquid-like. I mean, I don't know how to put it in words. What is the basic of this deconvolution? I mean, when you say that this is solid-like and when it is liquid-like for you?
Okay,
because usually we have a kind of system when, what is the criterion? Might be in this way.
Okay, so first of all, when you are coming to an NMR device and you have a known sample, you put it in and look at the FID signal. And honestly saying, all my experience that the really rigid part of, not just solid, but rigid part that is below glass transition temperature, they normally decay within 50 microseconds, even faster.
Okay.
Then something in between, so liquids, they start from some milliseconds, and what is in between, this is something soft or elastic. But the convolution can be done in 3 ways, and we involve all of them. So this is time domain, then you can the Fourier transform and you can get frequency domain, or you can try to make the distribution of relaxation times using some nice software from nice people. So there are actually three ways to do it.
But this is a kind of thing when this is, how to say, well visible, yeah? The separation is obvious. You just look at it and you see that. But what if you are somewhere in the gray area between? And how unique this thing is.
So this is, for example, how we try to differentiate amorphous and crystalline contribution. They are within the fast decaying part far before 100 microseconds here. In such a case, you know, for example, here, there are several approaches. The fitting of the spectrum, by the way, this is real spectrum. The fitting of spectrum or the fitting of the FID with the pre-known model, like here, like you see Gaussian model and Abrahamian or whatever. And just to confirm this guess, we sometimes simulate the samples with known crystallinity, or we refer to XRD measurements, and then try to correlate how we deconvoluted this fast line into, and then we get the really nice correlation, just linear. For example, we made it with method. This is sugar paper, for example. This is how we made it. So this is the way. Otherwise, you actually this is not spectroscopy. Sometimes this is not so obvious. This is actually obvious between water and the polymer. This is clear. And what is within the line, this is for each type of sample. You need to develop the approach. You need to develop the model. Then try to calibrate, and then of course you can use this approach for all the rest of your life, like we do with the polysaccharides, for example. And now also we do it with polyethylene and polypropylene. But for unknown samples, every time must be done some preliminary job.
So we should think about this jelly thing, what to write.
So exactly. So we will talk about this tomorrow, and we will talk more about this. How we do.
Thanks.
And Dr. Grunin, since you're already in this slide, as far as I see, like on the very top figure, there is this like curve-like thing in the very beginning.
Yeah.
What is the reason of such a behavior? Does it have a physical meaning?
It has the simple physical meaning. It has a very simple physical meaning. Then this is the red line. This is Pake doublet.
Yes.
If you here you see you have at least two maxima in the frequency. If you have two frequency, they will beat. They will have a beat. They will give you the oscillation. This oscillation comes from the actually Pake doublet, but it's not doublet because there are many protons are participating. Classical Pake doublet is for isolated pairs of spins, but here you have many spins and you have distribution of frequencies, and sometimes these guys have quite visible two frequencies, and two frequencies will always give you the oscillation. So this is the reason for this going down and then going up.
And physically, does it also represent a physical state of the system, like the presence of these?
Yeah, for most of the samples, for thousands of samples that we analyzed during many years of our activity, this tells about the crystallinity, crystallinity. But of course, there are some exceptions. Those guys who are below glass transition, even amorphous polymers can give you this type of oscillation if they're really far below the glass transition temperature. But normally for crystalline part, I will talk about this tomorrow, how to differentiate all of this.
Okay. So I think we already finished our time. So it is 4:15. So any other questions? Maybe a last question to Dr. Grunin?
Then everything is clear, I guess.
Yeah, we will have more questions, I think, as we discuss more applications and more, since this was like today, more basic stuff, we'll have more questions.
Yes, and what I would suggest, if those listeners who are participating now, you all have your own samples, your own tasks, or your own things to measure. So you can just create a kind of list of problems that you would like to resolve, and then we can think about this. This can be not only for these 3 lectures, but also for, let's say, for the rest of our project.
Yeah, we have some questions regarding this high resolution solid state NMR data.
Okay, Selena. Okay.
Yeah, we are struggling with fitting, Dr. Grunin, so it will be good to discuss it when you have time.
So what I discovered, Selena, actually your microphone is muted, I guess. Did you say anything?
Actually, I want to say that thank you for this great lesson. By the way, I learned a lot. about the J coupling and all. I can show you an example of our data. Actually, it's a little noisy, but it just looks like the examples you showed us. Can I show you an example?
Yes, I can stop sharing and then how to stop sharing, I don't know. Okay, I think I stopped.
Can you see my screen now?
So this is I do. I see.
Yes, we do, Selam.
Do you think it is too noisy? Do we need replications, for example, if we fit our data?
So is this spin check data or the data from the? This is other.
This is a high resolution data obtained from 300 megahertz, Selam, or 400?
400.
400.
I see some. So what type of samples is this? So this is allulose.
Yes, it's allulose.
You know, theoretically it can have such strange shapes. Sometimes, especially glucose is given an absolutely unpredictable shape of FID that everyone is looks and don't know what to think. But for this guy, do you have also signals from something like sucrose or like, I don't know, like starch, the same or whatever, just to be sure that the instrumentation is correct?
We have fructose, allulose, and glucose examples.
Oh,
and
glucose is not the best.
The data looks very good actually. The noise is really very small. I can show you. For example, for the glucose, it looks better.
You know, I'm not sure about the beginning of the decay, and I would think that we observe only on the rectified part of the signal, so that the long component maybe should go down, maybe not. I don't know. So, do I have these files?
I can share them with you.
You can share. You can share. I can look at them definitely.
It would be great. Thank you.
Yes, let's do it, Selam. So we are always standing for the perfect science.
Thank you. Thank you very much.
Okay, just share with me and we will go on.
Okay.
Okay, Mechit, do we need to say goodbye?
We can stop for today.
Mm-hmm.
So we are going to continue tomorrow to our lecture.
Mm-hmm.
So thank you, thank you first of all to you for the great talk, and thank you for the participants. So we will keep our discussion going tomorrow.
Yeah, it's important. Today we made the introduction. Tomorrow we will talk even more about physics.
Okay.
Ready? Yeah.
Perfect. Thank you so much.
Bye.
So,
Thank you.
bye-bye.